Okay, now today we will start a completely new chapter, different from sampling, signal samples, downsampling, which can be considered as the algebra of images or multidimensional signals. The new chapter is regarding the transformations. Let's go that it's about image transforms. Um, the concept of transformation must be accompanied by the concept of representation, image or any kind of a signal representation. Because without representing the signal, you cannot transform it. Think of it in the case of linear algebra. Think of a two-dimensional vector space. You have a vector, and as soon as you have a vector, we say that the vector, let's say the vector is x, is consisting of some elements, x1 and x2. Let's start with the two dimensions. But when you say it, when you state an entity, this can be a vector, this can be a signal, it can be an image, but as soon as you say it, you make an implicit assumption that it is already represented in the form of a basis, and that is x1 times 1, 0 plus x2 times 0, 1, for instance. So this representation helps us to come up with two numbers, two entities, x1 and x2. But they are actually corresponding to a representation on a frame that is expressed in terms of two basis vectors. What are those basis vectors? 1, 0 and 0, 1, the horizontal and vertical basis vectors. So these are the basis vectors. The basis vectors have some nice properties, like they are orthogonal to one another, and they have unit norm. Therefore, you don't have to scale x1 entity according to the magnitude of the basis vector. It is 1, therefore we keep x1 as x1. Now, in signal processing, in general, signals are also represented using basis signals. Of course, we can't say vectors anymore. It can be an infinite dimensional Hilbert space, and it usually is. It may be a continuous variation of signals. Let me start with a continuous variation representation of a continuous time one-dimensional signal. For instance, let's say x of t. When I write x of t and draw it or write it like this, I immediately make that the implicit assumption that I'm using a basis system, and that basis system corresponds to the time basis, consisting of impulses at different times. So x of t is essentially a linear combination of those basis signals. And what is that linear combination? It is from minus infinity to infinity, x of tau delta t minus tau d tau. You may find this not really looking like a linear combination, but essentially it is a linear combination of shifted and scaled impulses. This is scaled. So these are scales. So x of tau is actually a number. It's like this x1. x1 is a number, and x of tau is a number that changes for every tau. And by scaling delta t minus tau with that number and linearly combining in the form of an integration, if it is discrete, then it would be a summation. This would be my representation. I think in discrete time it makes better sense, so let's write it, because it's in the form of a summation, which more looks like a linear combination business of linear algebra. For all k, x of k, which is a number, times delta n minus k, which is a signal located at k. It's a shifted impulse. Now, starting from this basis, can you find a different basis? For example, let's say it is equal to y1 times 1 over square root of 2, 1 over square root of 2, plus y2 times 1 over square root of 2 minus 1 over square root of 2. Of course, these 1 over square root of 2, 1 over square root of 2, and 1 over square root of 2 minus 1 over square root of 2 are not chosen arbitrarily. They are forming another basis. Why are they bases? Because they have unit norm. If you take a look at the norm of it, squared versions of each coordinate is 1 over 2. When you add them up, it will become 1, and then you take the square root, it's again 1. So they have unit norm, and they are orthogonal to one another. If you take the inner product of these two separate vectors, it's going to give you 0. So these are indeed a basis vectors. But for these, of course, I have to find a new y1. So what is this? And a new y2. What is this? But with a certain choice of y1 and y2, clearly I can still get the same x vector here. This thing makes or defines the transformation. It's a transformation from x1, x2 to values with respect to one basis, which is originally usually the time basis, to a new set of values, y1, y2. So from x1, x2 to y1, y2, this link is the transformation. This is the transform that we're talking about. And image transforms, everything, including the Fourier transform, the famous, celebrated Fourier transform, is nothing different from this one. Now let's continue with the within the concept of signals. So if I can write x of n, if I can write x of n in a different format as a summation of, again, over k, or it may be an integral, it may be a summation, just some linear combination. It may be finite or infinite. So let's keep it like k, some summation of k, y k, let's say, times some different basis signals. Those basis signals are supposed to have some properties, and one property is they have to be a unit norm, and the other property is that different signals must be orthogonal to one another. For example, impulses, shifted impulses, are orthogonal to one another because they are at different locations, and we will define an inner product for understanding orthogonality, of course. Otherwise, what do we mean by orthogonal? What is an inner product of two signals? We will all come back to those topics. But for the time being, I can write it like ik. Let's see, g of this in this form. By the way, on my screen, my writing comes late, so I'm waiting for it. Okay, it arrives. If I can write x of n like this, then from the values of x of n to the values of yk, these y's, this would correspond to the transformation. And in that transformation terminology, this is known as the inverse transform kernel. Why is it the inverse transformation? Because actually the formula that we are looking at, the last one, is the inverse transform from yk to xn, y to x. It's the inverse transform. The transform should be from x to y. So it must give me a formula for what is y of n, y sub n or y of n, whatever, the index. What is this? This is the transformation. And it will probably be in the form of x of k, some different h sub k of n. And this h sub k of n is the transform kernel. Right now, it may look very much abstract, but when we write the Fourier transform as an example, it starts making sense. You may think of an example for this representation. An example would be the Fourier series expansion, where g sub k of n are actually complex exponentials, e to the jk omega 0 n. You remember that? So do you remember this Fourier series expansion? Ck times x of n is equal to, for all k, ck times e to the jk omega 0 n. This e to the jk omega 0 n is actually g sub k of n. It's a function of n, and it changes with k. It shows a variation with k, and for different k, these gk's are orthogonal to one another. Again, what do we mean by orthogonality? What do we mean by inner product? We will come back to that. And the formula to determine the Fourier series coefficients was, as far as I remember, it was something like this. No, it's not in the form of a summation. It's not in the form of an integral. It's in the form of the summation. So let's write it like 1 over n summation k x of k e to the minus j k omega 0 n. Why am I stuck at that position? I have an extension. I can extend the page. E to the minus j k omega 0 n. So this 1 over n could be considered inside this, because unfortunately the Fourier transform or the Fourier series transform kernel and inverse transform kernels are not normalized. They're orthogonal but not normal. In order to compensate for the scale, we have to use a 1 over n factor in either of the formulas, the red one or the black one. So the transform kernel is this, and the inverse transform kernel is this. Okay, this Fourier series or Fourier transform or discrete Fourier transform, FFT, DFT, etc., they are good examples for this transformation business, what's going on, which transforms everything from the time domain, excuse me, to a new domain called the frequency domain. But if you consider the linear algebra topic here, you see that my new basis function, the basis vectors, are 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, minus 1 over square root of 2, which corresponds to a 45 degrees shifting from here to here. So it's essentially a 45 degrees rotation. It's not a shifting, the angular shifting. It's a rotation that we have. Rotation. So when you check out the literature or some books, some people say that the Fourier transform, even the Fourier transform itself, including all other transforms, are merely rotations of the bases. So you rotate the bases in such a way that the new basis vectors are now something different. Excuse me. I have to close this. Sorry, let me put it in silent. These rotations will they will give you a new framework. It will look at the signal from a different perspective. Well, the original basis vectors were looking at the signal from a time perspective, and the rotated version of it, which are made by e to the jk omega 0, etc., will give you a perspective to look at the signal from a frequency perspective. But the frequency and the time information were already inside the signal. It is there. It is contained. The signal carries all the information. When you look at it from one perspective, you see it as a time signal. From a different perspective, you look at it as a frequency signal. So this is how we come up with the concept of transformation and inverse transformation. And if you remember, in discrete time Fourier series and inverse Fourier series, the expansion formula, this one and this one, these Ks are finite, and it is determined by the period of the signal. If the period is, let's say, 8, then the summation is K from 0 to 7. Okay, 8 numbers are contained. That is called a finite transformation, which can also be written in the form of a matrix multiplication. So what I mean is this: if you say, for instance, for example, the transform, let's say f of k, to be equal to n from 0 to capital N minus 1, so it's finite. Lowercase f of n, g of k and n. I could put k as a subscript, but it's just 2 parameters, k and n, where k is also from 0 to n minus 1. This is a finite discrete transformation. Finite extent discrete transform. Fourier series is like that. This fk is c sub k, for example, in the Fourier series expansion formula, which are the Fourier series coefficients. And gkn is e to the minus jk omega 0 n. So omega 0 is something that you have to know, but it is 2 pi over capital N. So let me write it. Omega 0 is 2 pi over capital N. So that's how we formulate everything. This finite discrete transform can be written in the form of an output vector, although I usually use capital letters as matrices with an underscore, meaning a matrix. Unfortunately, this is a vector. It's one-dimensional. That is a one-dimensional thing. And this vector, okay, think of it as a vector, is equal to the G matrix. Now this is a matrix because it has 2 parameters, k and n, times the f vector, which is the lowercase f vector, let's say the time vector. So when you multiply a length n vector with an n by n matrix, you come up with a length n, another length n vector, which is the transformation. And in discrete time or in computers, in digital signals, this is the signal. This is the signal transform that we will be talking about. It's still like the linear algebra. It is linear algebra, actually. And expansion of this thing into 2 dimensions, trying to make it a 2-dimensional transformation, would be like this. Now, from here, let's think of a 2-dimensional transform. The kernel numbers are increasing. Making it multidimensional is not a difficult task. it's like this: f of k1 and k2 is equal to summation n1 from 0 to capital N minus 1, n2 from 0 to capital N minus 1, f of n1 and 2, g of k1, k2, n1, and 2. Okay, now we are in a little bit trouble because I was able to convert the top red equation into a matrix vector multiplication format, but I'm unable to do it in this way. So I have to find some ways to do it. A possible expansion that we have is to make this a separable transform. What do we mean by separable transform? A separable transform is like taking the Fourier transform of an image by taking the Fourier transform of rows and then obtain a result, and then take the vertical columns Fourier transforms. So horizontal and vertical separate transformation processes, for example, makes a separable transform. Luckily, in many cases, people essentially come up with a one-dimensional transform, and they apply it to two dimensions, horizontal and vertically. So we don't really have native G of K1, K2, N1, N2. Instead, we have G1 of K1, N1, and G2 of K2, N2. And in many cases, G1 and G2 are the same. One of them corresponds to a horizontal transformation along the rows of the signal, and the other one corresponds to the column processing of the signal for the transformation. Now, if we have it like this, if we have this kind of a separability, then this F matrix can now be considered as matrix. This is a matrix this time because it has two parameters, two dimensions, two dimensional orientations. This is also a matrix, although I write it as a lowercase letter because it's before the transformation. Now I'm adopting the Fourier transform notation. Lowercase is time domain, uppercase is the Fourier transform like thing. And we are processing the columns, which is represented by G2. So the columns are being processed by G2, and the rows are processed by G1 in the form of a transposition. So G2F, G1 transpose, in the middle F is also a matrix. G1 and G2 are also matrices. These are all matrices. This is a separable implementation of a two-dimensional transformation. Okay. We will come back to this concept of two-dimensional transformation, but right now we need to consider how to find the inverse of the transform. So let's open the parentheses and let's think of the situation of, or not the inverse, but actually how to find the transform from the basis. How do we relate the basis signals to the transformation? How to relate basis transform. If you represent the basis vectors with vectors and stack them to become a matrix, the transform matrix is strongly related to that one as long as you are in the form of a orthonormal, an orthogonal transformation, if we're talking about, if these bases are orthogonal. Let's come back to the example of this one. But this time I'm going to give you some numerical or number examples. Oh no, let's continue from parametric examples. x1, x2 is equal to y1, 1 minus 1 with 1 over square root of 2 plus, I think this is an inappropriate way of writing things. So I'm putting the 1 over square root of 2, not a division, 1, 1, and y2, 1 over square root of 2, 1 minus 1. This was the first linear algebra example that I gave you, if you may remember. Now the problem is, what is y1? I asked you this. And what is y2? You may formulate a 2 by 2 system of equations, because x1 and x2 are actually numbers. There are two unknowns, y1 and y2, and there are two equations. With this format, you just have to write it like this: 1 over square root of 2, 1, 1, 1 minus 1, y1 and y2 is equal to x1 and x2. This is therefore, it's like the inverse transform, because I'm converting y1, y2 to x1, x2. X is the original time signal, y is the transformation. So this is the inverse transform. How can I invert the inverse transform? I can say that y1, y2 is therefore the inverse of this to the minus 1 times x1, x2. So this is the transform. And this is the inverse transform. Sorry, excuse me. I unintentionally closed the screen sharing. Okay, I unintentionally closed the screen sharing. Sorry about that. So these are the transform, and the inverse transforms. But there is an easy way for this particular example and for most of the other particular examples. Can you find y1? This is 1, by the way, although it looks ugly. Y1 with this set of equations, can you determine it from x1 and x2? And the answer is yes, as long as this 1, 1 and 1 minus 1 are orthogonal to one another, and they are orthogonal to one another, and they have unit norm. In fact, I can, without this matrix inversion and equation solving, I can say that y1 is, for this case, equal to the inner product of x and, let me give a name to this one, g1, let's say, vector, and g1 vector. If I take the inner products of these, I can find y1. Why? Can you see that? Let me show it or illustrate this availability on an example. So this is your signal vector x, and these two coordinate systems are 1, 0 and 0, 1 coordinate systems. And I am rotating it by some amount and still obtain another orthonormal rotation system. It may be 45 degrees or it may be different. Let's try to make it 45 degrees, like this. Now we know that x is equal to x is equal to x1 times 1, 0 plus x2 times 0, 1, which are h1 and h2, or e1 and e2. Let's not use h. I apologize for this. It looks like a filter if I use it like that. E1 and this is E2, the basis vectors. Now, if I project X over G1, this is G2, and if I project it on X2, what I find will be Y1 and Y2, because I can say that similarly, X is equal to Y1 times G1 unit norm plus Y2 times G2 with unit norm, isn't it? So what is Y1? It is the projection of X onto G1. That projection operator here is essentially giving me this magnitude. Okay. And similarly, Y2 is equal to X inner product with G2. So inner products seem to appear at all places, at all times. And it's easier to have an inner product than to have a matrix inversion. Matrix inversion is a hugely complicated task for higher dimensional signals, at least. For 2 dimensions, it may look easy. But essentially, it's way more difficult than having an inner product. And an inner product is simple. If you have a length 2 vector and another length 2 vector, X and G1 are both length 2 vectors, you just term by term multiply those things. In signals, we will in the future see that these inner product definitions not necessarily multiply term by term and add them up, but it takes the second term's conjugate if it is complex. Now we are looking at real axis, real values, everything is real. But notice that in Fourier transform, the bases are e to the j omega n or something like that, which is complex valued. So when you're taking an inner product, you just multiply and integrate, or you multiply and sum up, but you take the conjugate of the complex exponential, and that's why we have always e to the minus j omega n in the Fourier transform formula. Actually, the basis is e to the j omega n, and the conjugate of it is required for taking the transform. These are the transform values, y1 and y2. We will come, but first, let us see examples of bases and their applications to signals and images. And the example that I want to give you will be 2-dimensional, an image processing example. Let's jump to an image processing example. Let's think of a signal, and this example will also tell us the importance of transformation in signal processing and in image processing. Not only the Fourier transform, but other transforms as well. So 6, 10, 8, and 12. All right. So this is our 2 by 2 tiny little image. And these are the values of the pixels. It's a 2 by 2 image, but it's still a 2-dimensional example. That's why I'm trying to give this or emphasize this as an example. In time domain or in original space domain, spatial domain, it is essentially in the raster scan order, something like this: 6 times 1000 plus 10 times 0100 plus 8 times 0010 plus 12 times 0001. Now these tiny little 2 by 2 images in the raster scan order that I have drawn are actually basis images. The impulses in 2 dimensions. The impulses in 1 dimension were basis signals, and their shifted versions are making the basis signals. Now these make the basis images. And the basis image formulation that I'm thinking of is, this is an image, let's say U, and that is equal to a double summation with K and L, K from 0 to 1 and L from 0 to 1, because it's only a 2 by 2 case. And we have VKL, which are the scales, times A sub KL MN. So these A sub KL MN are the basis images. And VKL are the values, the scales that scale the basis images. As a linear combination of these basis images, I'm stacking them and adding them up, and I'm having, or I'm constructing my signal U. Can we show a few examples of what AKL MN are? For example, A0 0 basis image is 1000. A 01 basis image is 0100. A10 is, although I'm writing in uppercase a, actually they are matrices, as you see, and have 2 parameters for the variations of those: 0010, and A11 is 0001 in this notation. So A00 is a matrix, and the parameters or the arguments of the matrix are M and N. So the horizontal direction is M and the vertical direction is N, let's say. I'm just drawing them instead of writing those matrices. I'm putting them in boxes because they are essentially images, as we see. Now I'm trying to come up with a different basis image, set of basis images, and those different set of basis images I'm writing in red, and I'm going to call them B. Okay. For example, B00 is 1 over square, no, not square root. It is 1 over 2, 1, 1, 1, 1, and B01 is 1 over 2, 1, thinking 1, 1, 1. Okay. B1, 0 is, sorry, the bottom line is -1 and -1. Yes. And then this is 1, 1, -1, -1. And finally, B1, 1 is 1/2. This, I forgot to put 1/2 here. They are all scaled by 1/2. Why am I doing it? I will explain. 1, -1, -1, 1. I'm doing it because that 1/2 is essentially normalizing. If I take the inner product of B0, 0 with B0, 0, I have to get 1. So every value is 1/2, and there are 4 values. There are 4 values of itself. Every 1/2 I multiply with the other 1/2, which makes 1/4. 1/2 times 1/2 is again 1/4. I multiply all 4 of them. Each of them will be 1/4. I will add them up, and it will give me 1. The square root of it will also give you 1. So it's the Frobenius norm, the norm of this B0, 0 and B0, 1 and B1, 0 and B1, 1. They are all 1. They are unit norm entities. And when you take the inner products of one another, like B0, 0 inner product with B0, 1, in half of the cases, positive 1/2s will multiply with positive 1/2s. In other half, positives and negatives will be multiplied. So half of them will be -1/4, half of them will be 1/4. When you add them up, it will give you 0. So their inner product is 0. Whenever you have an inner product, B0, 0 inner product, B0, 1, for example, is 0, it means they are orthogonal. We are trying to have a unit norm and orthogonal, which in combined translates as orthonormal set. So this is an orthonormal set. Check by yourselves. Take the inner product of B0, 1 and B1, 0. It's just term by term multiplying every element and summing up. You will see that half of them cancels with the other half, and you will get a 0. So this is an orthonormal set. Now, can I obtain 6, 8, 10, 12 to be equal to something? Let me say y1, 1 times 1/2, 1, 1, 1, 1, plus y1, 2 times 1, 1, -1, -1, plus y2, 1 times, of course, there's a 1/2. I'm always forgetting these 1/2s. Excuse me for this. 1, 1, -1, -1, plus y2, 2 times 1/2, 1, -1, -1, 1. So what are these y1, 1, y1, 2, y2, 1, y2, 2? Okay. If I can find them, it means I am transforming 6, 10, 8, 12 into a new set. And I said that these are orthonormal. This set is orthonormal. We found it to be like that. The example is already constructed that way. So do you remember what y1, 1 is? How do we find y1, 1? We take the inner product of x and the corresponding G1, let's say. So we have to take the inner product of the signal, which is 6, 10, 8, 12, with 1/2 in parentheses, 1, 1, 1, 1. How do we take the inner product? The inner product is simply obtained by term multiplying and summing up. So this is equal to, y1, 1 is equal to 6 plus 10, 16, plus 20, it is 36, divided by 2, because there is a 1 over 2, it's 18, right? This is 18. How do we find y12? It is x inner product with g2. So the top terms, 6 plus 10 is positive and positive multiplied by 1. And the bottom terms are multiplied by negative ones. So it is 16 minus 20, which is minus 4, over 2 is minus 2. And this one is the left side numbers are added, which is 6 plus 8, that is 14. The other one is 22. Their difference is 8, isn't it? Yes, their difference is 8 divided by 2. This is equal to 4. And this one is equal to minus 4, by the way. So let me correct it. And this one is, we add the diagonals and we subtract from the off diagonals. 6 plus 12 is 18. 8 plus 10 is also 18. This is 0. So instead of 6, 10, 8, 12, now my new image is, after this transformation, my new image is 18 minus 2, 4, and 0. This is the transformed image with the new basis images. The idea is, in some cases, efficiency, in some other cases, to observe some features. We take the Fourier transform of signals to see what kind of edges appear, and we want to know or have an understanding about the frequency content, okay? But sometimes another application, for example, may be compression, data compression. The first signal, the red signal, is very inefficient for compression. If you just, for example, chop off, make a lossy compression by chopping off signals. Suppose that you drop this 12, because we don't have a bandwidth to transmit 4 signals, 4 values, 4 integers. We have a bandwidth to transmit only 3 values. It requires a 3 to 4 compression. So we get rid of 12. How much error do we make? We make a squared error, which is equal to the square of the number that we lose. That is 12 squared, 144. If furthermore we get rid of another signal value, let's say we get rid of this 10, then it is 144 plus 100, the error that we make. We are just, if we don't send or transmit a signal, it means that in the receiver side it is replaced by a 0. So that is the square distortion, mean square distortion that you make. It's very bad. It's like you have an image and you are cropping some portions of the image because you cannot transmit them. Would you make this kind of a compression? That would be nonsense. You're cutting the image, transmitting this self because your bandwidth is not enough. You don't do it that way. It makes a lot of distortion, error. Instead, you first transform and then you start transmission. And if your bandwidth is not enough, you can get rid of this 0, for example. And how much error do you make when you don't transmit a 0? 0, because its value was already 0, and the receiver will reproduce it as 0, and the distortion will be nothing. You have already sacrificed 1/4 of the data without sacrificing the distortion or quality. Let's say that, unfortunately, the situation is worse. You have to get rid of 1 more sample, and you can only send two samples. Let's get rid of this one. in the order. How much error does that make? What is the square error that you make? It is 0 square from one of them and -2 square from the other one, which is 4. So let's make a comparative distortion. In one case, it was 144, and then it was 244 because it is 12 square plus 10 square. And then it is, on top of this, you make a distortion of 8 square, which is 64, and that makes 308. And finally, 36 more than that, which is 344. I guess. I may make some numerical mistakes here, so excuse me for that already. And for the other side, the distortion by this much compression, the analogous type of compression, was 0 because it was already 0. If I chop off another signal, then it would be 4 because -2 squared is 4. If I chop off one more, then it would be 4 plus 16, and that is 20. Unfortunately, if you chop off everything, including this one, you have to come up with the same result, 344, probably. I didn't check, sorry. Because the energy are the same. Energies before and after the orthonormal transforms are the same. This is also known as the Parseval's relation. Nice, isn't it? The Parseval's relation say that the power or the energy in time domain and the frequency domain are the same. It doesn't have to be the Fourier transform. It can be any orthonormal transform like this one. The energies are the same. But of course, it means that you're losing the signal completely. Except for that, for all other cases, as you see, chopping off after the transformation gives you infinitely better distortion, infinitely less distortion. That's why we sometimes make transformation. And you may remember that in image processing, a famous compression standard is JPEG. And in JPEG, they use discrete cosine transform, which is also very efficient in pushing, compacting all the energy towards the top left corner, like this one. So this may be the DCT in 2x2, who knows? Well, I know, and it is indeed. But in 2x2 case, the transforms are all the same. The Fourier transform is also this one. So this is the only useful transform that we have in 2x2. It pushes the signal power to fewer coefficients around the corner, and all the others are having less or smaller coefficients corresponding to better distortion or smaller distortion when you sacrifice them. So this may be a motivation about why we are taking the signal transforms, why we are having the transforms. I said that the distortion is 0. 0 is obvious because it was 0, and when we reconstruct them, it will clearly be 0. But will the distortion be really 4, 20, and the other one is also obvious, but 4 and 20, I didn't verify. I just said that the distortion is the same as the square of your sacrificed magnitude. But I didn't prove that. This is valid only for orthonormal transforms, and it requires a verification. But we have to stop at this point. We will continue. We will not continue next week because I will be submitting the exam. I will put it on the Canvas web page. But I decided to do the class next week You won't be responsible for the things that we will cover next week, but next week we will do a class because we are doing online, so it's a little bit making us late. So we have to hurry up a little bit. Let's make a class next week at the same hour, at the same address. Although I cannot announce it from Canvas, or maybe I can. We will do the class, online class. And the exam will be just a take-home exam, so class hours will not be a problem. And in that class, I will show that when you put y11 is 18, y12 is -2, or 0, I chopped it, I make it 0, but the other magnitudes are the same. By that compression, is the distortion, mean square distortion, really 4? Square distortion, is it 4? Or when I crop two of the items, or 3 of the items, including 0, -2, and -4, will it make really a distortion, a squared error of 20? We will have to verify it. Until next week, you may start working on it already. Maybe I ask it as a homework question. But we will go through these ones. Are these really the correct distortions that we have? We will see that. So one important final remark: next week is the exam week, and I will submit the exam questions on Canvas. And next week we will still do the class on the class hour starting at 9:30 still, because the examination will be take-home examination, so we don't need the time for that. Yeah, my wife, who's also a lecturer in the environmental engineering, gave me a warning that you could have duties if you are assistants for exams of other people. Now, I ask you if any of you in this class is an assistant who may have an exam duty at this hour next week. Can you have, is there a possibility that you may have an exam monitoring duty? But that's not related to the course, so I stopped the recording for the time being, and after that you may give the answers. So I'm stopping the recording now.